Today we're going to finish up our sort of study of indirect addressing buckets and heaps and so on and so forth. And this week we'll finish up data structures and we'll move on to at least a little bit starting to look at max flows, which is our next topic. But we do have a little bit more to do on heaps. Last time we did a lot of exploration of how being able to indirect address into arrays lets you speed up the performance of monotone heap data structures. And I showed you how to use certain ideas from tries to get this DiNardo and Fox version of, we sort of went beyond Dial's algorithm and sort of used it recursively and with some good lazy amortization to improve the running time of our heap data structure all the way down to order m plus n log c over log c for shortest paths. And basically to get a sort of a log c runtime on delete min, and essentially log c and a similar log c runtime on insert and decrease key. So that was great. And then I mentioned briefly that Goldberg, Cherkassky, and Silverstein recognized that we had these arrays and we were scanning the arrays in order to find the next non-empty entry in the array, but that really is a min finding problem. So instead of scanning the array, you should use a clever data structure for it. And they, in specific, took the whole DiNardo and Fox data structure and put a heap on top of it. So they use a sort of a more standard binary heap to manage the highest order port differences between values in the queue. And then for each small range of values, they use the DiNardo and Fox data structure. So they called these, heap on top or hot queues. And I mentioned a couple of things. First of all, that Silverstein was a grad student who dropped out and became the first employee at Google and is now a billionaire many times over, but still doesn't have a PhD, poor guy. Also, Goldberg is somebody I encourage you to read if you want to see how to do implementation experiments with algorithms. He's written a lot of beautiful papers studying various data structures, comparing different heaps and search trees and so forth, and also, in particular, studying various max flow algorithms and shortest path algorithms, different varieties, min cost flow, shortest paths with negative edge weights, so on and so forth. But besides making a bunch of important algorithmic contributions, he's really shown how you design good experiments to assess the performance of algorithms in practice and understand the roles of heuristics in practice. And basically, he is the canonical model for if you want to do an implementation project in this class where you're studying the performance of some algorithms, his papers show you exactly how to do it. So I recommend that. But we're going to go somewhat farther with heaps. And this idea that finding the minimum in a big array is just a heap problem. And we're going to see that we can get much more recursive on it than just putting a heap on top of the very top of the priority queue. So today I'm going to show you something known as the Van Emde Boas priority queue. Which is named after the inventor, Van Emde Boas. Perversely enough, this was developed in 1977, before all of the algorithms that I showed you last time. Right? So you don't always get this sort of continuous improvement in running times. Sometimes you get sort of different ideas going off and giving you different things than just a pure runtime improvement. The best way to explain the Van Emde Boas priority queue is just to show you the very simple structure and operations. Now, I say simple. It is very simple, but you have to do it exactly right or it doesn't work. And it's a little bit strange how sensitive it is. So typically, when we talk about a priority queue, we say, well, there's this minimum, and we'll keep track of it, or we'll keep it on the side, or something like that. And the details don't matter too much. Like, you can have it in the priority queue, or you can have it somewhere separate and just pull it out when you need it. It doesn't matter. With Van Emde Boas, you really have to get it exactly right. So a Van Emde Boas queue is a structure. And sorry, I'll use the letter Q for this, is a structure which contains some fields. And this is a queue for some number of bits. Okay, so this just makes it easier notationally. But until now, I've been talking about integers in the range from 0 to c. Now I'm going to talk instead about the number of bits that you're using to represent your integers. So b is just log c from what we did last time. Okay? And so if I want to build a queue on b-bit words, I'm going to start with a single entry, q.min, holding the min element if the queue is non-empty. Okay. Secondly, an array called q.high, q.low, which is indexed by of queues on the low order bits in each of our buckets. So again, we're talking about a summary structure, right? We have a big array of buckets for containing items within a certain range. And the way this is going to work is that if we talk about our C-bit words, we are going to have square root of C buckets, each containing square root of C of the range. Okay. And so this is going to be a recursive data structure. So we're going to have root C of these summary of these subranges, and we're going to put a recursive queue on each of the subranges. Okay. And so that means that this array q.low is indexed by the high b over 2 bits of your keys. Okay. And so you're indexing on the high b over 2 bits, and then each of your queues, which is going to recursively contain a root C range, is a queue on the low b over 2 bits of the words in that range. Make sense? Okay. So basically, pictorially, right, you've got this whole array of size C. And now we're just doing our usual thing with the tries, where each array contains root C items of the entire C range. So you have root C buckets dividing the range of C items into buckets of size root C. Okay. And just as in our previous data structures, we're going to keep track of which of these is full and which of these is empty. And for every one that has some stuff in it, we will make a sub structure for containing the items in that bucket. Okay. And then we also use, whoopsie, yes, this is an array. And then we are also going to have a Van Emde Boas queue called q.high, tracking the non-empty buckets of the top of the array. So this is a queue on the high b over 2 bits of the numbers that are in your priority queue. Make sense? Except, remember that the current min is not kept in the recursive structure. Instead, you have a separate container for the current minimum element. And again, this turns out to be really important for your data structure not to be messy, even though it tends not to matter in standard priority queues. So is everybody clear on the structure that we've designed? Okay, so in order to verify that, let's think about the operations that we might want to perform. So one of them is insert. Okay. So I've got a Van Emde Boas queue. I want to insert an element x into it. For notation, I'm going to write x as x low and x high. So here we have b over 2 high bits. And here we have b over 2 low bits of x. So given this as the definition of the structure, how do I insert this item x into the priority queue? And let's assume that the queue is not empty, right? If the queue is empty, well, actually, what do I do if the queue is empty? Well, in that case, I just need to put x into the min holder, and I don't need to do anything else. Okay? But let's assume x is not empty. So what do I need to do? Yes? Good. So that's the right place to start, except I need to check one thing first. Because remember, the current minimum is not actually in the recursive structure. So what do I have to be careful about when I'm inserting a new item? Yeah? Yeah, maybe the item that I'm inserting is smaller than the current min. So the first thing I'm going to do is say if x is less than the current min, then swap them. Okay? So now I can assume without loss of generality that my x is larger than the current min. Okay? So now I proceed to do what you just suggested. I need to sort of look separately at the high and low bits. Okay, so I'm going to insert x in the recursive structure. And what that means is I'm going to look and see if the bucket where x belongs is empty or not. Right? So if there's already something in the bucket, okay, if q.low indexed by the high order bits is non-empty, what should I do? That means there's already some stuff in the bucket associated with the high bits. Right? So what do I need to do to finish inserting x into the queue? Yeah? Yeah, I need to add the low bits to that non-empty queue. Okay, sorry, let me be consistent with my terminology. This is insert. Now, you said insert x, but I'm just going to insert the low order bits. This makes things consistent because remember, this is a queue for b over 2 bits, and XL has b over 2 bits. And remember that I sort of know what the high is because of which bucket I'm looking in. Right? So I can put the high order bits and the low bits together to get all of x back. Okay? We'll look at that when we do a delete min. Okay? So if the bucket is non-empty, I need to insert XL into the bucket, and I do that recursively by putting it into the queue for that bucket. Okay? What if this bucket is empty? Then what do I need to do? Yes? Exactly, right? If this bucket is empty, it means that there is no key that has this high bit, this high bit value, right? And so we have to instantiate a queue for that collection of high bits, okay? And so actually, let me do that first, right? We're going to create q.low of xh containing xl as its min, right? There was nothing there before, so we need to make a queue to hold those low order bits. And then, because that bucket is no longer empty, we need to insert xh into q.high, which is our queue of buckets. Right? So that's the whole insertion algorithm. Does that make sense? And again, it's just like what we did with the tries, right? We have this array of buckets. We're keeping track of which buckets are not empty, and we are then recursively storing things into the structure for the appropriate bucket, just like we did for tries. A question?
When we state that q.low is an array of queues, are we assuming these queues are also like vanity as like queues?
Yes, we are going to be. So this is where this structure gains its performance, is that it's Van Emde Boas all the way down. We're not just sort of layering a queue on top of the top level of the data structure or anything like that. Okay. Any other questions? Okay, so my question is, what's the runtime of this insertion operation? Okay. So let me start by leading you down the wrong path so you can correct me, right? It appears that at least in the worst case, in order to solve a b-bit problem, we're doing 2 recursive calls on b over 2-bit problems, right? So that would suggest that t of b is equal to 2t of b over 2 plus order 1, right? Which would suggest an order b runtime. I put question marks around this because it's wrong. Okay. Now, how is this wrong, given that we do, in fact, do 2 recursive calls? Yes?
Because if you're creating q.low of x of h, that it's like, oh, one word. You stop that.
Exactly. So, you know, in this branch, we only do 1 recursion. That's great. In this branch, we do 2 recursions, but one of the 2 recursions is trivial because we are creating a queue with 1 element in it. Okay? So this is constant work, even though it's creating a whole data structure. Okay? And that means that, in fact, the time to insert a b-bit word into this data structure is just the time to insert a b over 2-bit word plus order 1, which means that the runtime is order log b. Okay. Yes? Yeah, we get this mess. I mean, I think you could still force it to work, but it would be incredibly complicated to just define the algorithms with all the special cases that you need to check about if there's only one thing, or who knows. I haven't tried because it's so elegant this way. Okay? But you see why it matters to have the minimum element out, is that is why you can rely on one of your queues being empty when you do this insertion. Okay. Let's do the converse. How do we implement delete min? Okay. Well, with delete min, we already have the min. Right? The problem is that when we delete it, we need to replace it from the recursive structures. So how do we determine what the new min is going to be? Well, let's take care of one easy case, right? If there's only one item, then the result is an empty queue, right? If the min is the only item, then we've emptied the queue. So let's assume that there's more than one item in the queue. Okay, so how do we figure out what the new min is? Yes?
Low queue, like for the lower bits.
Which queue should I look? Oh, you're saying look into the queue for the minimum element. Okay, so I can look there and see, and if I do look in that queue, I know that that bucket is the minimum bucket that's non-empty, right? Okay, but if that bucket is empty, then what do I need to do? Good. So if this is empty, I'm going to need to look in the high order bit queue to find the smallest queue with the smallest non-empty bucket. Now, this will also work if there still are things in this bucket, right? Either way, if I just start by checking q.high dot min, okay? So I need to know what is, again, I'm doing a find min first as opposed to delete min, right? I'm asking what is the smallest set of high order bits that exists in the recursive data structure. So notice this is asking, like the minimum element is not in the recursive data structure. So I'm simply asking, of all of the other elements, what is the smallest collection of high order bits, right? So I'm going to ask if there is something in the min container of the q.high, right? If it's null, it means that there are no other elements, right? I.e., this is the queue becoming empty that I mentioned before, right? So I can just return, yes, I've deleted the min, but my queue is now empty, okay? So I don't have another replacement. And so I'll just store null in q.min. I'll probably throw the data structure away, but that's not so important. Okay. Otherwise, this yields the smallest non-empty bucket, which I will call, and the half key associated with it, namely xh. Now that I know that smallest non-empty bucket, how do I finish finding the replacement minimum? Yes? Recurse where? Like, where should I look? I've got these high order bits. I've got b over 2 bits of the current minimum. Where do I find those low order bits? Yes? Exactly. I look in the low order queue, or sorry, not check, right? Q dot low of xh contains the minimum element in that bucket. Right? So I will delete min from q dot low of xh. To finish finding q dot min. OK, so in this step, I've deleted an item from a bucket. What might happen? Yes?
It's empty.
Right. So deleting from a bucket may leave me with an empty bucket. Right? If q dot low of xh is now empty, what do I need to do to get a proper representation of my data structure? Yes? Sorry, what was that? Exactly. I need to delete min, i.e. delete xh, because that is the min, from q dot high. Because remember, q dot high is supposed to keep track of the non-empty buckets. And so if I've made an empty bucket, I need to take out that bucket from q dot high. Okay. So what's the runtime of this algorithm? Well, the story is much the same as for insert, which is no surprise because it's just running insert backwards, right? So in the case, I mean, we do a recursive delete min on a b over 2-bit data structure, right? And if we're lucky, we're done, right? If there's still things in the recursive data structure, we don't have to do anything else. But it's possible that when we did this deletion, we emptied a bucket. So it looks like, again, we're doing 2 recursive calls, right? And so we're back into that 2t of b over 2 problem. So how do we argue that that's not a problem for delete min? Yes?
The delete min took a long time.
Exactly. If we do this, that means that the first delete min, which happened up here, was from a size 1 queue. Okay. And so it was order 1 time. Okay. So again, 2 recursive calls, but one of them is constant time. So again, time for a b-bit word is equal to time for a b over 2-bit word plus order 1, which is order log b. OK, what's the big deal? I mean, last time I showed you log c runtime, and now we have a log b runtime. What's the difference? Yes? B is log c, which means that this runtime is actually order log c. It is, in fact, exponentially faster than the priority queues that we saw last time. Okay? I actually saw this in print in the New York Times last week. There was some article which talked about how the whatchamacallit, number of people driving or something like that was getting exponentially larger. And that always makes me so grumpy when they misuse exponential, right? But here it actually is an exponential improvement. Now it's an improvement from log C to log C. You might say, what's the big deal? Log C is already small, right? But that's what you care about in data structures, right? In data structures, everything is logarithmic. And so getting something that is doubly logarithmic is a really impressive improvement. Especially if you think about it nowadays, right? Modern architectures, right? So C might be, there might be 128 bits in a machine word. There certainly are 64, right? So log C is actually a meaningful improvement over C. Okay. Now, there is an issue with Van Emde Boas Q, space. So how much space do I need to represent this data structure that I described for you? Yes? O of C. How come? Well, so remember that I don't actually need to create these recursive structures unless they're non-empty, right? So that's going to be bounded by n, right? I'm not going to, or n times something, right? I'm not going to need to create an unbounded number of these, okay? But I'm certainly going to need to create this top-level structure, right, to contain the top-level buckets. And if you think about how it's being used in the Van Emde Boas queue, right, what do? I look in q.high to get some high-order bits, and then I just need to go look. I need to find in constant time the corresponding queue. So this is for the low bits. So this is going to be an array of size root C. Okay. So the space is going to be at least square root of C if I use an array to help me find the appropriate low-order buckets. Okay. And again, I just said C might be 64 bits or 128 bits, right? Do you really want to use, gigabytes and gigabytes of array storage for your priority queue? Now, there's a fix for this. Any thoughts? How might I get order 1 lookups without having to waste all of that space, which is mostly empty? Yes? Hash table, right? The fix for this is a hash table, which coincidentally is the next topic we're going to study. Okay? Just a coincidence, I assure you. But we are going to study hash tables rigorously and formally, right? When you study them in elementary algorithms, they usually tell you, well, just assume the keys are random, right? And then everything is fine. But you can't assume keys are random when your advisor is providing the input. They're going to be adversarial, not random. And so in algorithms, it's understood that to make a hash table work, you either add randomization, which is what we are going to do. So your algorithm starts flipping coins. Or you have to pay a slight slowdown. It's not actually order 1 time anymore. Okay? So if you're willing to use large amounts of space, then the Van Emde Boas is a deterministic order log C time data structure. It's kind of great. If you want to save space, you have to pay a small penalty of either using randomness or using a little bit of extra time. A couple other things I'll mention about this. Thorup, in 1996, he improved the running time of Van Emde Boas queues to order log n, where n is the number of items in your queue. Okay. Now, have to be a little bit careful about this. Van Emde Boas queues assume that the keys are integers, right? And so does Thorpe. So his algorithm is designed for integer keys that are fitting into a machine word. But the time no longer depends on how many bits are in your machine word. Okay? Yes?
One and the Boas space and fusion space.
I don't remember if he incorporates fusion trees. Fusion trees were the first data structure to do this. So there's a long line of research on, again, data structures that manipulate bits, that work in machine words. They exploit the fact that you can do constant time operations on a machine word, right? We're already relying on indexing into an array in constant time, which is one of our machine word operations. When we start doing hashing, we'll be talking about addition and multiplication of machine words in constant time, right? So this is an assumption of our computational model, is that operating on a machine word takes constant time. And Van Emde Boas relies on this idea that you can operate on a machine word in constant time. And he relies on it in order to eliminate the explicit dependence on the number of bits in the machine word. Okay. And he also shows a really interesting, once you improve the running time to depend just on the number of items, that means that you can use Thorpe's algorithm to sort machine words in order n log n time. So you're breaking the time bounds for sorting, again, by relying on the fact that they are integers. But all of the elementary algorithms for sorting integers tend to take n log c time. So Thorpe's algorithm is significantly better. He also shows actually an equivalence. He shows that if you have a data structure that is a fast heap, you can use it to sort, but also if you have a data structure that sorts fast, you can use it to make a fast heap. So it's quite a nice paper. Question? Oh, it's by Thorpe. And it appeared in 1996 at SODA, I think. I'm sure there's a journal version that came out later, but I don't remember where it is. Okay. One other thing I'll mention is that I called this the Van Emde Boas priority queue, and that's what everybody calls it. But in fact, it turns out that it is more accurately called a Van Emde Boas search tree. Because in addition to implementing insert and delete min, you can also implement predecessor and successor in order log b time. And so you can use it for the same things as you would use a binary search tree for, but again, with an exponential improvement. And this will be on your homework this week to actually make that improvement. And you don't have to change the data structure very much. And it's pretty much this, you sort of use the same kind of thought about how to do these operations to avoid two recursive calls. Okay? So that's the story of heaps and indirect addressing. Any final questions about that topic? No? Yes? To doing log c time for predecessor and successor? No. This will be on. I don't think that I put that question onto this week's homework. It's going to come out on Wednesday. Okay. So you're welcome to start thinking about it early if you've already finished the other problems. Yeah.
How good can you do with hash tables?
So with hash tables, you really do achieve order one lookups into the top level summary structure. Oh, so with randomization, and this will be our topic after break, with randomization, you can achieve, you can do all of this in order n space. Okay? So it's optimal space, it's space optimal as well as being really fast for time. Now, I don't think we know that it's time optimal. You might be able to do better. Remember, there's a project at the end of the semester, so you can feel free to think about that. All right? Okay, it's a little earlier than usual, but since we just finished the topic, this seems like a good time to take a brief break.
square root buckets, but it seems like that doesn't show up in any of the time complexities. Kind of confusing.
Because it's an array, right? Because you're only indirect, like you never have to scan the array. You just need to look up a particular entry in the array, and that's constant time.
So so how does square root?
So the point is that there is this array of square root of C buckets, but you never need to scan it. You just need to put things into specific entries of it and take things out of specific entries of it. Right? So inserting an item into an array is constant. And so is deleting an item from an array or looking up an item in an array. Okay?
Yeah, I thought what would we get if we combine one Emde Boas trees and fusion trees.
Yes?
So for one Emde Boas trees we have log B complexity.
Yes?
And for fusion tree we have log B of n complexity.
Yes?
Which is log n
Over log B.
over log B. So
Yes.
we get
Root log B. Yes. Well, that's the kind of timeout that we got in the original fusion trees. I think that it was already doing something like this.
That's awful.
How do you like writing on these sheets of paper? Is this like these
It was the first paper that showed that you didn't always need explicit dependence on but I think it might have been log n to the 2/3 or something like that. It's been a long time since I looked at that paper.
I feel like I really like leaf paper.
But that was kind of the idea, was that you,
Well, I just-
like,
I don't think I could do
we
it.
know you have to have,
I was
for a long time people were thinking, well, you have to have
Well, this
bits,
is
and
maybe
so
not a problem.
we might as well express the runtime.
I feel like having a
But
notebook is just
Fusion Trees were the first people who said,
and, like,
no,
if I
maybe
have
we can
to
stop worrying about how many bits there are as long as we know that it's a
paper,
constant time
this is,
operation.
like, kind of annoying unless I have a big here. I don't like that.
Yes, very funny bit operation.
Was it so?
It's way easier to erase. Like iPad,
Why is it kind of
but I feel like iPad you have to toggle around things to erase.
No, we just like.
In real
Yeah, iPad is kind of annoying. I don't know.
But you can like move things to like if you want to like erase something. Actually,
It's like you convert the amount of time you put in. So if you care about grades, you can do that. Like you have to turn it on.
Sorry, I couldn't stand up. I was like,
I'm the
isn't it also O of n log C? Like, so like the measure is O of n, is that what you said?
I think like actually like there's like
So like the naive way, there's like log C log C.
I don't like I wouldn't take it.
Wait, really?
Wait, I think all you said about the naive is that like
Okay. Clearly there's no need for this break. Everybody's sitting down, so I might as well start up again. So a couple of logistical things. First of all, there are a bunch of Jewish holidays coming up. The next 4 Mondays, 3 of them are Jewish holidays when I won't be able to lecture. My inclination, in order to keep the class on schedule, is to do something that we did, I think, with good success last year, which is we will hold class. I mean, that is, people can come to class, and the TAs will play a recording of me presenting last year. But we'll be watching for hands and we'll pause the video and answer questions in real time. So hopefully this will provide some value over just watching the video by yourself, which you are also welcome to do. Okay? Any questions about that or feedback on that? No? Okay. Let's see, thing 2. Years ago, I took a HAS class, so to speak. I wasn't here, I was at Harvard, but it was a class on Chinese history, and the professor there required every student to come to his office and chat for 15 minutes so that he could meet every one of them. This was pretty impressive, given that I think there were like 350 students in the class. I'm not going to impose that sort of requirement, but if any of you want to introduce yourselves and tell me a little bit about what you're interested in, I would certainly be happy to meet you and hear that. So you should feel free to do so. All right, so as I start on the next topic, just a quick little poll. Well, I'll start with the easy one. Who has seen hashing before? As I expected. Now, who has seen a sort of theoretically rigorous analysis of hashing without any assumptions, say, about the distribution of keys and things like that? Who's actually seen formally how to use randomization to make hashing work? Ah, interesting. Okay, it's usually a larger number. So I just wanted to know how fast I should go through that portion of it. So yeah, so our next topic, which will occupy us today and some of Wednesday, is hashing. But hashing is going to become a vehicle for looking at randomized algorithms. Oh, again, I got a question during break, which is not good. I should get them during class so everybody can benefit. What are we relying on here? What are the benefits of using this array? Well, in the implementation of insert and delete, we need to take a set of high order bits and immediately jump to the appropriate bucket, that is the queue associated with the appropriate bucket. And so that relies on the indirect addressing functionality that given those bits, we can just look at the appropriate entry in the array. Okay? So given a key, we can store something associated with that key, or we can retrieve something associated with that key in constant time. Okay? Now, I actually glossed over something, which is that in order for this to work, we want the array to be initialized, right? And if you think about it, you might worry that just filling this array with zeros costs you root C, right? And over here we talked about how creating a queue would, like we do all this creation of empty queues and things, right? Is that going to add a root C to the time bound? It turns out that you can simulate an initialized array without actually initializing it. And this is a problem that I sometimes put on the homework. I don't know if I will do it this year or not. But essentially, there's a trick where you use 3 arrays of size n to simulate an array that has been initialized to all zeros, a single array of size n that has been initialized to all zeros with no initialization time at all. Okay? And so you can use that in the queues. But those operations, right? So insert, delete, and lookup on a key, on an integer key, in order 1 time, are operations that are trivial with a sufficiently large array, right? The whole idea of hash tables is to get that in small space. So they're really just a space-saving technique. They don't provide any new operations better than the ones that you can already get with an array. Okay. So what do I mean by randomized algorithms? Well, I teach a whole course on this, which I encourage you all to take the next time I teach it. It probably won't be this spring. The idea of randomized algorithms is what you can do to improve the performance of your algorithms by having those algorithms flip coins while they're running. This makes their performance unpredictable, which can be very annoying for the person who's trying to debug them, but can also be very powerful in avoiding the worst case that an adversary is trying to push you into. So if the adversary who's creating the inputs for your algorithm doesn't know what your algorithm is going to do, then it becomes a lot harder for them to create worst case inputs. And so there are many cases where adding a little bit of randomization makes your algorithms much more effective, improves their performance by a lot. Okay. Now to emphasize, this is not about assuming anything about your inputs. Okay, so it's often very easy to build good algorithms that run well if the input is random. Okay, that is not what we are assuming. We are still going to be pessimistic and assume the worst about the inputs that our algorithm get. But we are going to intentionally flip coins while the algorithm is running in order to work around those worst-case inputs. Is that distinction clear? OK. So again, our model is, we're still in this model of integer keys that fit in a single machine word. Okay. So just to make that concrete, let's assume the keys are the integers from 1 up to little m. Okay. And that means that the word size is log m. Okay. So we can, if we want to, store everything, like if implement these operations using an array of size m. Okay. But we are going to assume that we're working with n items, where n is much less than m. Or equivalently, we're going to talk about having just s space, where s is much less than m. You'll see later why I distinguish these. But we're basically going to ask, if we have a few items, can we store them in relatively small amounts of space and still achieve the really fast runtimes that we seek? Okay. And in addition to the indirect addressing that we've already been using to take advantage of arrays, we are also going to use arithmetic operations or other bitwise operations. So things like being able to add 2 words or multiply 2 words. And we're going to assume that all of these things can be done in order 1 time. Okay? So we're asking for more than we get with the bucket-based heaps. Okay? So again, we want to store our items, which are keys in the range from 1 to m. We want to store them in an array whose size is a lot smaller than m. Okay? So the idea is to find some sort of function, which we'll call a hash function, mapping my keys into a smaller table. Right? And now I can store my item x in bucket h of x. And this gives me back what I had from arrays, right? When I get a key, I simply compute the hash function, and that tells me what bucket I should look in to get the information about that key. Now, this imposes some requirements, right? We need h to be fast, right? The computation of h is now a part of every lookup, every insertion, every deletion. So we have to worry about the time that it takes to compute h. But that's not the only issue, right? If I pick some fast function h, like h of x equals 1, that's pretty fast to compute, right? What do we have to worry about? Yes?
Or about hash collisions.
Right. So the problem is that, as defined, we might end up mapping multiple keys that we're storing to the same bucket. Several keys in the same bucket. Now, in terms of correctness, we can fix this pretty quickly. We can just put in a linked list per bucket to deal with the fact that more than one item might be in the bucket. But what might result? What might go wrong? Yes? Right. Now the search time is proportional to the list length, right? So this is the whole issue with hashing, is that we're going to use this idea of a hash function, but our goal is to keep the number of collisions small. Okay. So can I come up with a hash function that will be guaranteed to have a small number of collisions? I mean, there are some pretty complicated functions out there, right? I mean, surely I could, use something fancy like MD5 or something and just guarantee that none of my items collide. Yeah?
I feel like if M is a lot bigger than S, there has to be some set of, just by the sizes, there has to be some set of things that makes you have a lot of collisions.
Right, so just by the sizes. So people who've taken 6042, what's the reason that there are going to be collisions no matter what function you use? Pigeonhole principle, right? So the pigeonhole principle says no. Right? For any function, there exist inputs that will cause many collisions. Right? If an adversary knows what my hash function is, then they can pick all of the items that map to a single bucket as the input. And so now all of my items will be in one bucket, and I've been reduced to using a plain old linked list. Yes? So how do we fix this? Our fix is going to be to look for what's called a hash family. So let me put this on a different board. Our fix is going to be to design something called a hash family, which is a collection of functions such that for any input, there exists a good function in the family which causes few collisions. Okay. So now, again, we'll go beyond this for later, but for now, let's sort of assume that we are given our items and we just have to hash them for fast lookups later. Let's not worry about changing over time, right? Changes, inserts and deletes. But at least we might hope that, given a set of items, I can pick a good hash function from the family and use that to nicely spread out the items into my buckets, right? So do we have confidence that there is a hash family that we can use? Like, is there some set of functions that we can use that would guarantee that no matter which input you had, there would be a good function in the family? Yeah?
You could do all of them.
All the functions, right? So for example, I could say, I get my n items, and I want to put them into n buckets. So what will I do? Well, I'll take the function that sorts the items and puts the smallest one in the first bucket and the second smallest one in the second bucket, and so forth. And this function perfectly spreads. It's called a perfect hash function, right? It puts all of the items, one item per bucket, right? So good hash families exist. Now, what is the problem with that particular hash function that I just described that sort of sorts the items and tells you where each one goes? Yes? Too slow, right? So our hash family needs to be fast. the functions in our family have to be fast functions, right? So, I mean, even forgetting about finding the right functions, once you have it, right? If we're going to use that sorting function, how long does it take you to evaluate that function on a given input? Well, if you think about it, you're basically looking for that item in a sorted list, right? So it takes you log n time to evaluate that function, and again, that makes your lookups cost log n instead of costing 1. Okay? And in fact, if we think about that a little bit more, the hash family needs to be small. Okay? So basically, if you are going to be picking a function, the time that it takes you to pick the function is sort of information theoretically going to be proportional to the number of to the log of the number of functions that you have. Okay, so picking a function from the family or computing the function will take time proportional to the log of the number of functions. This is fuzzy. We'll be more clear about what that means later. But this is kind of like the sorting lower bound that many of you have seen, right? If I need to choose among a large number of functions, sort of each step that I take sort of gives me one bit of information about which function I'm using for most things that you can imagine doing. And so if I have a really gigantic collection of functions, it's just going to take me too long to kind of search my way through that space of functions to decide which one I'm computing. Okay? So we want functions that are computable in constant time and that can be specified in a small amount of space. Because again, if I need to know which function to use, I have to write it down somewhere. And in order to use it, I have to read the description of the function. So if the function takes many machine words to specify, then it's going to take me a long time to look at all of those machine words in order to know which function I'm supposed to use. Okay? So how can we come up with some good functions? Well, let me throw one other idea here. And this is going to let us start actually thinking about randomization. Let me ask what might happen if we just pick a random function. Okay, this does not meet all of the criteria that I just gave, but let's think about it anyway. Okay, so we are taking our set of n items, and we want to, and we use a random function that maps those items to my S space. How good a job is this going to do in terms of collisions? What might I expect? And that was a pun, because the way that we analyze randomized algorithms, the first thing that we always look at is expectations. Suppose that I have some item x, and I want to know how long it's going to take me to look up that item x. Well, that's going to depend on the number of other items that land in the same bucket, because I'm going to have to scan through that linked list. And so that's a question of expectations. So how do I compute the expected number of other items that is going to collide with my item x? So I think, as I said in the description, this course does require some basic probability. It basically requires you to know 5 things about probability, and we'll see, I think, all of them, all but one, today. Okay. Yes?
Like n over s, if they're everything has size s. So like you could have an indicator random variable
Good.
for each of the n items, and each of the n items, like because you're just choosing a random function.
Great. So the quick intuitive answer is going to be n over s because your n items are being divided among s buckets, and so you figure an average of n over s items per bucket. But to formally analyze this, I'm going to introduce an indicator variable, and this is one of the key concepts. I will write cxy equal 1 if x and y land in the same bucket. Okay. Actually, sorry for my notational consistency with my notes. Let me call this Cij. Okay. And so now the number of collisions with item I is just the sum over all j of Cij, right? That's just counting the number of items that collide with I. So this is key idea number 1 from probability. Okay. How do I evaluate this expectation of a sum? Yes? Right. So this can be evaluated as the sum of the expectations using the next key idea, which is linearity of expectation. Okay. So I've simplified this. Now I just need to know the expected value of one of these indicator variables. So what's the expected value of xij? Yes? Good. So there are n of these indicator variables that I'm summing, 1 for each j, or n minus 1, right? And the value of a single indicator is just the probability that I collides with j. Right? And since items are being mapped uniformly at random, the probability that that happens is 1 over s. And so I end up with n minus 1 over s collisions in expectation. Okay. So is that clear? Yes, question.
Why did the Cij become an Xij?
Oh, thank you, because I typoed. That's the usual answer to why anything. Yes?
Why is it n minus 1 and not n?
Because I'm asking for the number of collisions with item I, and that is sort of implicitly ignoring item I colliding with itself, right? You could now, if you're interested in the number of items in the bucket, right, you know that I is in its own bucket, so the actual size of the bucket is going to be 1 plus the number of collisions. Okay? But that's only plus 1. Asymptotically, it doesn't change anything. Okay? Good question. All right. So a random function gives me this bound on the number of collisions and suggests that, well, if I just make s bigger than n, then this will become order 1, and I'll get the order 1 lookups that I want. Yes? So that's great. Now the problem is that if I use if I want to use a truly random function, what do I have to do in order to describe that function? Well, if the function is truly random, it turns out that pretty much the only way you can describe it is writing down its value on every point. Okay? So you would have to say, for every one of the m possible values, what does it hash to? And you'd write down a random number. So you'd be basically writing down m random words that represent where every item should be mapped, which means that your storage space would be m, which defeats the whole purpose of using something smaller than an array. Okay? So that's not a good idea either. Okay. So a purely random, or a purely random function takes too much space. Okay. We want a really small function that hopefully we can just describe in a couple of machine words. Okay. But if you think about it, if I'm only writing down a couple of machine words, that's only room to describe a polynomial number of functions, not the exponentially many functions that exist. So we really need a small hash family. And Carter and Wegman introduced this idea of what they call a two-universal hash family, which has the characteristics that we want. Okay. The key insight is that we don't need an entirely random function, because if we look at our analysis, which was very short and very simple, it did not rely on everything about the function being random. Right? The only thing that we really cared about at the end of our analysis was the probability that one item collides with one other item. So the only events that matter to us are events involving just two of the individual items that are being hashed. Okay. And so this draws us to another idea of pairwise independence, which has turned out to be very powerful in theoretical computer science. We say that a collection of variables are pairwise independent if, for every pair of them, the pair of variables are independent. Now, this may seem like just a circular definition. What's the difference, right? If I'm just saying every pair is independent, what am I leaving out? The answer is that I'm not worried about larger sets of variables being independent. So as a particular example, suppose that I want to generate 3 random coin flips. Okay. So I'll have coin 1 and coin 2, which are both normal, unbiased coins. But instead of flipping a coin for coin number 3, let's look at the XOR of coin 1 and coin 2. Okay. So coins 1 and 2 are, by definition, independent of each other, right? The outcome of coin 1 does not affect the outcome of coin 2. But I claim that, in fact, coin 1 and this pseudo-random coin 3 are also independent of one another, that knowing the value of coin 1 tells you nothing about the value of coin 2. Why is that? Sorry, knowing the value of coin 1 tells you nothing about the value of coin 3. Why is that? Yes?
Regardless of the value of coin 1, there's a 50% chance of either outcome.
Exactly. Since I'm XORing the coins, whatever coin 1 is, there's a 50% chance that coin 3 is the same, and a 50% chance that coin 3 is the opposite. So the distribution of coin 3 is 50-50 unbiased, no matter what the value of coin 1 is. And the same is true for coin 2 and versus coin 3. So any pair of these coins are mutually independent. Okay. But coin 3 is actually deterministically, right? Can be deterministically given coin 1 and coin 2. So the 3 coins are not mutually independent. Is that clear? So this suggests that it might be possible to achieve pairwise independence without needing a fully random function. Okay? And it turns out that you can do that. So the two-independent family which I will denote by h sub ab. It involves two parameters a and b, which will each be a machine word. What we do is we're going to pick a prime number. So this is the only bit of number theory that's going to show up in this class. You can also use a prime power, but we're going to use a prime p, which is in the range from m to 2m. And we'll sort of fill in why we want it to be that way later on. Now, we will pick a random pair of numbers, a and b, from the numbers mod p. Okay. Now, what's nice about the numbers mod p? Why are we working with the numbers mod p? The numbers mod p are a field. Okay? That is, if you think about the numbers mod p, I mean, we all know how to add and multiply mod p. But it turns out that if you work modulo prime, you can also divide modulo. So we also know how to subtract mod p. But with a field, you can also divide mod p. Okay? There is a unique solution, mod p, to any formula of the form ax plus b equals y. Right? Or sorry, to ax equals b, sorry. Which we can call b over a. So you can divide modulo p. And if you don't know why that's true, don't worry about it. I don't really remember why it's true either, even though I took algebra years and years ago. Yes? You get close enough to this to get what you need for a two-universal family. Okay? But like I said, I'm going to concentrate on primes because they're easier to work with. Okay? All right, so we've got this field. We're going to pick two numbers from the field. And now we are simply going to define the hash function on x to be ax plus b mod p. And that's it. Okay. Now notice that we are picking a random pair of coefficients and then multiplying by it. Okay. So the value of HAB of x is random. But it's not random because x is random. We're assuming nothing about the keys that were given. We are introducing randomness in the value of the hash function. Yes?
The hash family is parameterized by the random choice of p?
P is not random. P can be chosen to be any fixed prime of the suitable size. The hash function is parameterized by these two integers a and b that we have chosen. Okay? Now, my key claim is that for any pair of numbers x not equal to y, HAB of x and HAB of y are pairwise independent. And uniformly distributed. So regardless of what keys you're given, the hash values for those keys look like independent random numbers in the range from 0 to p minus 1. Okay. And the proof of that is literally 60 seconds. So what is the probability that HAB of x is equal to some number t? Or is equal to some, yeah. Well, that's the probability that AX plus B is equal to t. which is equal to the probability that AX is equal to T minus B, which is the probability that A is equal to T minus B divided by X. And so here is the first place that I'm using division modulo P, right? This is a unique value in the range from 0 to P. And the only way that you end up with a particular value for the hash function is if you pick the appropriate value of A. And since I'm picking A randomly in the range from 0 to P minus 1, this is just equal to 1 over P. Okay. Now, the other thing that we need to check is the probability that HAB of X is equal to some S, and HAB of Y is equal to some T. So again, we can do the math. This requires that AX plus B is equal to S, and AY plus B is equal to T, right? I can write this as a matrix equality. Right? Whoops. Which is basically asking for this matrix formula to be true. Yes? Well, do I know that this matrix formula has a solution? Well, from your linear algebra, we know that the solution exists and is unique if the determinant of this matrix is not 0. But what is the determinant of this matrix? It's x minus y, which is not 0 because x is not equal to y. So in fact, there is a unique solution to this matrix equation that satisfies this outcome, which means that the probability that it is chosen, remember, A and B are the parameters that I choose, is just 1 over p squared. So for any pair of possible outputs, the probability that you get that pair of outputs is 1 over p squared. In other words, it has the same probability distribution as purely independent choices of bucket. Okay? So this is the key trick in true universal hashing, is to make the keys look random even though they didn't start out random. Okay? Now there's a few more details of this that I will fill in next time, and we'll give sort of the details of this implementation. And then I will show you how to make it go even better to, instead of having just expecting a constant number of collisions, I'll show you how to get 0 collisions in something called perfect hashing. And that'll be the end of our data structure unit. So I'll see you on Wednesday.